Well, thank you. So in this talk, we'll give you an overview of Clang, pretty much a continuation of the previous tutorial about LVM, but now focusing specifically on Clang itself. So just out of a curiosity, basically, how many people in this room have never touched the Clang code, never even dared to look into the Clang subfolder yet? Well, it's like half the room, basically. So this tutorial is for you, basically. So what we're going to do is we're going to give you an overview of the Clang architecture, and we're going to do that by taking a simple C program through the different components of Clang. Then we'll describe a bit how you can work on the Clang source code itself and how to test Clang and stuff like that. As we end the tutorial, we've been simplifying the reality a bit because there's just too much to cover. Clang is not a trivial piece of software, so we had to make some simplifications here and there. But it should give you a good idea of the Clang overview itself, the Clang structure itself. A little bit about us. So both of us work in the Mali GPU OpenCL compiler team in ARM in Cambridge in the UK. Anastasia is the co-owner of OpenCL in Clang. So if you ever submit a patch that's messing about with OpenCL supporting Clang, basically she's probably going to review it. Both of us have been working with the Clang code since like 2014, so for 5 years. Doesn't mean we are experts. I wouldn't say so. It's like every time we touch something different, we feel like we're total beginners still. But we're going to try and do our best in giving you an idea of what Clang is. So the structure of this talk, we're first going to give you a little overview of Clang, how it's organized. Then we're going to take a look at the individual components of Clang and see like how they act when we're taking a simple C program through that. Then we're going to describe a bit how we work, you can work on the Clang source code, how to test it and stuff like that. And then we'll open up for questions. And I'd recommend that we keep like the questions to the end because we have so much to cover, so much to get through. So okay, let's get started, basically. So the Clang project, it's part of the LVM monorepo these days, which you can find on GitHub. It's consisting of like 21,000 files at the moment. That might sound a bit overwhelming, but actually like 18,000 of these files are little test programs, so it's overall not too bad, maybe. The core of Clang itself is consisting of like 21,000 files, 830,000 lines of code. And then there's another 33,000 lines of TableJen definitions. And Clang supports like a whole variety of different languages and dialects, as long as they're like based on C or C++. There's actually two kind of variants of Clang, as you may say. Basically, Clang is a compiler driver, and Clang is a language family frontend. So they're actually different kind of things, but both of them are referred to as Clang normally. The compiler driver is the thing that's mostly known by people outside of the Clang community, I'd say. You might often see claims like Clang-3 is doing a really great job on this file, or maybe it isn't. And it's actually not Clang which is doing like the real optimizations. It's the LVM transformation process which are doing all these optimizations. But Clang gets the credit anyway, so that's nice for Clang. The driver itself is responsible for like driving all the different phases in a compiler run, like driving the preprocessor, the linker, optimizations and stuff like that, and also making sure that all the flags are set correctly and pointing to your kernel, your installation. The other side of Clang is that it's a language family frontend, and that's going to be the main topic of this tutorial. And the purpose of a language frontend is like compiling C-like code to LLVM IR. The language frontend is going by some different names as well. So it's known as CFE, which is C frontend. That's like an older name. Or CC1, Clang CC1. And we might use these terms interchangeably. So the language frontend is basically the main topic of this tutorial. But before we dive into that, we're just going to give you a quick idea of the compiler driver. So this is like the textbook compilation pipeline of a C, how to compile a C file to a binary, basically. So you have a C file on the left, you pass it some flags. The C file goes to the preprocessor, which does all the macro expansion, does the include file handling and stuff like that. The result of that is massively expanded, and that goes into the front end. Front end produces some kind of intermediate representation. The middle end takes over and does optimizations, transformations on this intermediate representation. Eventually, it will go through the back end, which is going to produce assembly instructions. And assembler will assemble these into object file. And then the linker will run and possibly combine multiple object files into a single binary. If you run Clang on any input file, you can actually tell it to print all the different phases that it's going to do, or all the different steps of the compilation pipeline it's going to run through, with the -CCC print phases option, which you see here. So if you just say Clang some file.c, the first thing it's going to figure out is like, oh, you passed me a C file, so that's the step 0 basically that you see. So it's understanding that, oh, this is a C file, it's an input, so what am I going to do with that? Oh, I might need to run the preprocessor first on that, so that's step 1. That will produce preprocessed output that goes into the compiler, step 2, that's going to produce IR, and so on and so on. So you can see there's kind of a one-to-one mapping really between the classical textbook compilation pipeline of a C program and what Clang actually decides to do when you pass it a C file. Now actually doing all these steps as a separate step basically, like running preprocessor, then saving the file and then reading it back in and running the front end and then saving the file again and reading it back in, so on, is kind of inefficient. So the next thing it does basically after figuring out what it needs to do is combining all these different steps into some tool executions, and ideally fewer tool executions so that you don't have to like write out your intermediate state all the time and read it back in. And Clang has a special option for that, --###. And to make it easy to remember this option, I've heard some people call this the toilet brush option for obvious reasons. What you see here is basically it has condensed down this whole pipeline into 2 steps. Namely, first it's going to run the CC1 front end, which is going to take the C file and run on that. And you see that it's like passing a whole lot of options. So the initial invocation is just Clang factorial.c, and from that it's expanding it into a whole lot of options, like setting, first of all, calling CC1, so instructing Clang that we now want to run the front end. Then it's passing a triple, which it deduces from whatever your current host system is currently and what it was built for, and so on. It's passing some include paths. And this is only a fraction of the options it's actually passing. The other tool it executes is the linker, LD, at the bottom. And again, it's like passing a whole lot of different options to the linker to make sure that it does what you expect it to do, basically. That is pretty much all we were going to say about the compiler driver in this tutorial. So let's talk a bit about the front end then. So the main task of the front end is to take any C-like code and compile it into LLVM IR. But actually, Clang is doing a lot more than just that. It's also trying really hard to emit helpful diagnostics, so that whenever your input program is not correct or has some syntax error or whatever, that the user can easily see what's wrong with that and then fix it accordingly. Over time, Clang has been supporting lots of different languages, different standards and dialects and so on, and making sure that all of these are supported at the same time is a challenge by itself, I suppose. What's also important is that any source locations are recorded nicely, so that when you have your final binary and you're debugging it in your favorite debugger, that you can easily map whatever you're doing there back to the original source code. And last but not least, Clang is also a foundation for many other tools which need to work with C or C-like code in some way. So think of syntax highlighting, code completion, refactoring tools, and so on. So that was a little overview. Now let's dive a little bit deeper into the front end. So we've got our compilation pipeline again here. And I've highlighted the two blocks on the left, the preprocessor and the front end, because that's what the Clang front end is really doing. And after the front end, it's really done with it, basically. And we're going to describe these two blocks by taking this simple example through. So simple factorial function. It contains a recursive call. Nothing too special about that. So let's zoom in a little bit into these two first blocks, basically. So in Clang, the preprocessor and the lexical analysis are kind of combined together. So that's basically the very first step of the compilation. Reads in your C file, preprocesses and lexes it. That will result in a stream of tokens. Then the parser is going to interpret these tokens and try to build up an AST for that. There's a sema component which is going to do the semantical analysis to make sure that when something is parsed, that it's actually also semantically correct. When all is fine, it will produce an abstract syntax tree or AST. Then the cogent component is going to take that AST and traverse it and produce LLVM IR. And then Clang is basically done. And then it's up to the rest of LLVM to do the rest. There's a bunch of other classes that are used in various ways here. So for example, there's the target info class, which is responsible for containing all the all sorts of details about the target you're going to compile for. Because the LLVM IR that's produced by Clang is actually already target independent. Think of, for example, pointer sizes that are bound to your target that you're compiling for. There's the Diagnostics subsystem, which is used throughout the compilation pipeline. Whenever there's something wrong, basically, it will fire Diagnostic to the user. And then there's other classes like line options and source manager. The Diagnostics will go a bit more into that later. So let's get started with the lexer first. So as I said, the main job of the lexer is to take the C file, which is a stream of bytes essentially, and convert it into a stream of tokens, where tokens are like, it's kind of a compactor representation of a sequence of bytes. So if you have, for example, the sequence int, standing for the type int, after lexing, it's just a single token which specifies like, oh, you saw the keyword in, basically. Now, this initial step is kind of performance critical, because imagine you have a large project with lots of include files and stuff like that. And if you run the preprocessor on all these things, you expand all the include files, all the include statements, for example, you get a massive file. So the lexer is actually clever in that way. It's going to do the preprocessing at the same time as it is going to do the lexing with some clever tricks. And that allows it to have some special fast paths as well. So if there's a big if0 block or if some include file has already been included, it will find out and just quickly skip over that. It also supports tentative parsing. So sometimes the parser is like requesting tokens, and then at some point it realized like, oh, I can't really parse this with the rule I was trying to parse, so I need to unparse it basically and try another parsing rule. And that's basically supported by the lexer as well. So just to give you an idea of how this lexer thing really works, so Clang has an option where you can actually inspect the different tokens that are being produced by the lexer, which is -xclang -dump tokens. So let's see what it does for our simple input program. So the first thing it sees is are the characters int, int. So basically, int is a keyword in C, C++, and so on. So it's returning the int token, It's like recording some extra information that this is the first token on the line, start of line. And then there's the location information on the far right. The next thing it sees is factorial. Factorial is not a keyword in C or C++ or anything, but it matches a certain pattern called an identifier. So the lexer will return the token kind identifier with an extra value factorial. There's actually a little space between the int and factorial, but like most of the time you're not really interested in these kind of little white space details when you're parsing a program. But the lexer is still recording it by annotating the identifier token with leading space flag, basically. Next thing it sees is open parentheses or left parentheses and so on. So basically, with this you can see what the lexer actually sees. A little bit about the internals. So all the different tokens that are available are declared in token kinds.def. So here you see a couple. We've got if, inline, and int. They're all keywords in C languages except for inline. Because here you say basically inline is only defined for C99, for C++, and for GNU extension modes. And the keyword is basically not available in any other language modes. The parser is the main consumer of what the lexer does, basically. And there's like a close interaction between the two while you're taking your C program through. So we've got this function consume token inside the parser, for example. And at some point it will call lex, which means like really consume this token and advance to the next token, basically. And then there's also a function like try consume token, which will try if the current token is actually of something you're expecting. And if it's not, then you say, oh no, you can't consume this, maybe try to parse something else. And if it is, then you just consume the token. And that's the lexer. And now Anastasia is going to talk a bit about the parser.
Yeah, right. So let's have a closer look at Clang parser. First of all, it's a handwritten recursive descent parser. What happens is we will have to look at the sequence of tokens that we get from the lexer, and we will look at them from left to right, and we will apply grammar rules from top to bottom. There are obviously a lot of grammar rules to select from in C or C++ or other languages that Clang supports. And in order to select the rule, parser will look at the tokens ahead and try to see what is the next matching rule to apply. It will also perform tentative parsing, which means it will try to parse tentatively until it fails. If it fails, it backtracks. But if it doesn't fail, it will continue into, and at some point it will complete the parsing and match the grammar rule. Clang parser will try to recover from errors if they are encountered during parsing, and it will try to parse as much of input source as possible. And that's just simply because we would like to give as many diagnostics as possible in one invocation of a compiler instance. And it's also sometimes just helpful to understand what's wrong with the program if you see multiple errors. Typical recovery points, if you encounter an error in parsing, you're obviously sometimes in a state that you can't actually proceed parsing. But at the boundaries of statement, you can just recover parsing and carry on parsing. Also, something special about Clang parsing or in general diagnostics, it will try sometimes to provide you hints to tell how you might fix your program. And that can be very helpful. However, it only happens on some of the cases, and normally they are quite simple, but they are still very helpful. Right, so let's come back to our example and talk you through parsing in Clang. Here you can see the call stack of basically just breakpoint in one of the parsing procedure, And the entire call stack is visualized here, apart from we did skip a couple of frames just to make it simpler. We start from CC1 main function. That's an entry point to Clunk. And just to point out, the first few frames are actually not part of a parsing. They belong to the compiler driver. As we explained earlier, Clunk is also a compiler driver. Then the first entry point to the parsing is parse_ast function. And from there, we will start to match the grammar rules. And as I mentioned, we go top-bottom, top to down. We will apply the top-level rules first. In this example, we have top-level function definition. And therefore, the first rule that will apply is parse function definition. And that's how it is defined in the spec, in the grammar rules as well. Then we will recurse further down into parsing compound statements. So as you can see, where we end in the function definition grammar, we will have a compound statement to parse further. So here is how the grammar looks for the compound statement. We start from the opening brace, and then we will have to parse a list of either declarations of statements. And the first statement we have is an if statement. Then we will have to parse the expression in the conditional if statements. And expressions are actually, there are so many expressions in C spec that it's very kind of complicated and convoluted how they are defined the rules. But the idea here is we start from top level, which is a just generic expression, and it's represented as comma-separated list of either assignment expression, and then you recurse further down. And then at some point, if we're parsing this particular condition in if statement, we will have a relational expression rule that will match. And you will have right-hand side and the left-hand side, and you have comparison and equal operator in the middle. And if we are parsing right-hand side of our binary expression, as it is displayed here, we are parsing an integer literal 1 in this case. The end rule is a primary expression, so that's the end of the parsing. And at this step, we know that we successfully matched grammar rule for parsing binary expression. Right, so once the program is parsed, we know that it's syntactically correct. The next step will be to actually check validity of this program semantically. And there is a special component in Clunk that does that. It's called SEMA. SEMA and Parser are very tightly coupled together. There isn't any in-memory format that they exchange. However, there is certain interface that they use. And SEMA is the biggest client of diagnostic subsystems. So where most of errors and most of complicated diagnostics specifically actually are going to be handled in SEMA. Let's have a look at our example again. And if you remember, our last frame was parsing right-hand side of binary expression. And as I mentioned, we successfully parsed the rule, matched the grammar rule in this case. And we are now ready to construct an abstract syntax tree representation of this particular operation. But before we do that, we actually call SEMA method. And typically, the interface between parser and SEMA is using act on parsed entity member functions of SEMA. So how does the SEMA architecture look? The first thing SEMA will do, it will check validity of a program from the semantical side. For example, even if you are parsing successfully binary operator in C, you might not be able to perform the operation if the types that are operands in this operator, if the types aren't arithmetic types, you can't actually perform the binary operation. So here is how the check looks like in the Clang code base. You basically just query the type. Is it arithmetic type? If it isn't an arithmetic type, then you will call invalid operands method of SEMA. And what this invalid operands method do, it will just call a special helper function diag. And that function allows you to handle errors in the Clang source code. I'm going to come back to the diagnostics, how they work, and this particular helper function in just a few minutes from now. So let me just finish with flow for the semantical checks. So at the end, if you don't have any diagnostic, or if maybe the diagnostics aren't severe, you will end up with creating an abstract syntax tree, and that's simply done by constructing abstract syntax tree node, just invoking a constructor regularly. As in this case, we are constructing a binary operator, and we will parse left-hand side and right-hand side to it. Just to point out, this image here, picture how SEMA actually works, is really idealized. In reality, there are very few places where SEMA actually works like this. You will see a lot of different flows where the AST can be created first, and then the checks are performed. And the diagnostics might be given multiple times in the flow. And there are multiple reasons for it. Sometimes it's just simpler to create an AST and use AST API to query extra information about your program and then provide diagnostics. And sometimes it's for other reason. For example, in C++, we have such functionality as templates. And in templates, you often have to delay the diagnostics until the instantiation of a template. Therefore, you have to actually parse and create an AST first, and then the diagnostic will happen later on. Right, so let's look at the diagnostic subsystem in a little bit more detail. The purpose of diagnostic is to communicate to the programmer that something isn't right in the program. And there are several severity levels. You can have notes of warning. They aren't really harmful. They're just informing you about something that might be harmful. But if your program is incorrect, you will get an error, and the compiler will bail out with no output. Very important is to give the precise source location, because that will help developer to understand where to fix the issue. And I think one of the biggest art for a front-end developer is to provide very concise but informative diagnostic message. That's often not that easy to do. All the diagnostics are defined in a special files, TableJen files. We're going to talk about TableJen files in a little bit more details later. But just to point out, for the diagnostic, the name for these files is normally diagnostic something kinds.td. And there is a helper function diag. I already mentioned it, and I'm going to show an example here. So let's come back to our example. Let's assume we mistyped the return type of our factorial function. And if we compile this code with Clunk, it will provide an error, unknown type name I. This error is defined in diagnostic semakinds.td file. And I have to say, most of the errors are defined in this file. If you check the size of the file, that's the largest file for defining diagnostics. And this is the notation that we use. So we have the ID, some kind of identifier of diagnostic. Then we specify the severity level, and the message comes next. Then in the source code of Clang, we can refer to the ID of the error message. We actually will never have a string that displays error message in the Clang source code, in the C++ side of it. You will only find this in the TableJen files. So here's an example. We are using diag helper function, and we are going to pass the ID of our error message. We are also going to pass the source location, because it's important to provide some source information. And we are also going to pass one extra thing. The Clang diagnostic system is quite fancy. It actually has a lot of parameters and a lot of fancy things you can do with it. You can look it up later, but here's one example. You're passing a parameter, and what you can pass here is a parsed identifier of our type. And it's often very helpful to output this information from the source directly in the diagnostic message, because it allows to understand problem code much easier. Right, so once we parsed our program, it's semantically correct. What happens next? We create abstract syntax tree, which is a very close to the source representation of a program. There isn't actually anything that you lose at this point from your original program other than comments and formatting information isn't preserved. But everything else is encoded in this representation. Clang Abstract Syntax Tree is mostly immutable, so once you create it, it's really difficult to modify it. Apart from some special cases, for example, for template, we provide functionality to kind of perform some modification, but other than that, it's not very easy to change once it's created. I'm going to present a couple of key classes that are used in Abstract Syntax Tree area. You can look up the full diagram online. I have to say, if you follow this link, you will see the full hierarchy of classes of Clunk, not just Abstract Syntax Tree. And there are more than 1,000 classes there. But a lot of them will actually belong to a representation of Abstract Syntax Tree. So one of the key concepts is representation of type, and there is a special base class for representing types. From which there are several concrete subclasses, such as built-in type, represent a built-in integer type, for example, and there are also pointer type or array types. If we are using a qualified type that we haven't actually used it in our example, but if you are writing something like const int, then the representation of this in the AST is call type, and this call type will have a reference to a type that is being qualified. Another key class is statement. That is a base class for representing statements in general, and there are several concrete instances, for example, if statement or return statement. Expression is derived from statement, and there are also several concrete instances. Particularly those we use in our examples are integer literal or a binary operator. There is one interesting, which is decal ref expression, and I think you will see it in absolutely every program you compile. And that is just a way to refer to some previously declared object and refer it in the current expression. One statement I haven't introduced yet is decal statement. Everything which contains declaration will be represented as decal statement, and it will have reference to decal. And that is a base class to represent any type of declaration in your source program. But for example, in our case, we have function decal, and we have also parm var decal, which is a parameter declaration that is derived from var decal. And var decal will represent any variable declaration. Let's come back to our example. Clunk allows you to output abstract syntax tree representation of your original program using AST dump flag. And that's actually very handy. It's mainly used for front-end developers, but sometimes it might be useful just to understand the input program. So we can see here we have function decal first, and it has parm var decal, which is a parameter of a function. And then next we have compound statement, and inside we have if statement. If statement, condition of if statement is a binary operator in this case, and we have our decal ref expression where we are just referring to a previously declared parameter n, and we have an integer literal as a right-hand side of our binary operator. So as you can see, it's a very, very close representation to the original program, quite intuitive to understand. So if you have an abstract syntax tree, you can use visitors to traverse it, and it's actually a really important concept in front ends in general. And it will allow you, for example, to perform extra analysis and provide maybe extra diagnostics of your program, or you can just perform even some operations or some manipulation, something fancy. There are 3 types of visitors that are widely used. For example, recursive AST visitor allows you to visit full AST. Statement visitor is used for statement or expression visited, and then we have type visitor for types. I'm going to talk a little bit more about visitors, showing it on the example of cogent. And I'm going to pause for now and switch to cogent. So cogent is a final step in a front end, and what it does, it takes an AST, it will traverse it, so it will use visitors to traverse the abstract syntax tree, and it will emit an LLVM IR as it goes along and visits the tree. Just to point out, not to be confused, LLVM also has cogent, but it's a different cogent because LLVM's cogent will generate machine instruction, and Clang cogent just generates LLVM IR. As I mentioned, it uses visitors. It's also using a helper class to generate LLVM IR, and that isn't part of Clang, it's part of LLVM, but Clang is using it in cogent phase quite a lot. And it also uses target information quite a lot as well, because it needs to make sure that the IR is being generated is compatible with targets that we are compiling for. There are two key classes in cogent module. It keeps the state of an entire program. For example, it will keep LLVM type cache, and that's very, very useful to speed up compilation. In each program, you are likely to use the same types over and over again. It's very difficult to write a program where every expression has a different type. So in order to avoid generating LLVM types over and over, we will use a type cache, and we will look up types and use them from the cache if they're already generated before. The cogent module also emits global and shared entities, and the next key class is cogent function, and it actually keeps state per function, and it generates function statements mainly. Let's come back to our example and see how cogent works. So we start from emit top level decal, and the first thing we are emitting here is a global function definition. Then these two methods here actually belong to cogent module, but then cogent module hands over to cogent function because we are generating function definition. So we will start emitting function body and compound statement. We will first emit if statement, and we will attempt to emit the condition of if statement. And something to point out here, we will first use the visitor because we would like to visit the expression inside if condition and perform IR generation for this expression. The visitor is actually derived from Clang statement visitor that I introduced earlier. The first concrete visit method will be visiting binary operator, left equal in this case. And that's how it looks. Inside, we actually there are a couple of more functions that we invoke, but we will come to emit binary operator. And because it's not the leaf node of our tree yet, because we still have a left-hand side and right-hand side to visit, we will recurse into visiting methods again. And if we are generating right-hand side, then we will reach at some point visit integer literal, which is a leaf node and AST. And what it does, it will just call a builder helper function getInt, and it will generate an IR representation for integer constant. And here's our example. Clang allows you to inspect LLVM IR, and you can use emit LLVM flag to output the IR for your program. And for example, we were generating integer literal 1, and here how it looks in our output, nothing surprising, it's still 1 in LLVM IR as well. And it appears in compare less equal instruction.
Right, so now we have produced the LLVM IR. Basically, that concludes our journey through the different components of Clang. So let's have a look on how you can actually work on the Clang code base itself and how you can test it and so on. Just to give you an idea where you can find all these things. So the key thing to look for basically is the lib subdirectory, which is kind of similarly structured to all the components we've just been going through. So you see you have lib AST, you have lib cogent, lex, parser, and so on. Then there's the test directory, which is similarly structured basically. So individual tests for every different stage. And finally, there's the utils TableJen directory, which contains the Clang TableJen. I'll go a little bit in detail later. How would you get started, basically? You need to build Clang. You need to be able to build Clang. There's a getting started guide on the internet. Mostly the thing you want to do is pass this special option to CMake, dash the LVM enable project equals Clang. That will make sure that Clang will be built when you build LVM. And then you just run make, and then it will give you a binary after a while, a Clang binary. What's actually happening under the hood is that it's first going to build Clang TableJen. Then it's going to run Clang TableJen to convert all these magic.td files into some kind of C++ code. So that actually, these include files are then going to be included by the Clang source code places. And then it's going to build the rest of Clang, basically. Because now that we have all these include files as well, we can just build the entire Clang. So that's like what's happening under the hood. And that's mostly of interest if you're ever going to look into doing something with TableJen. So what is this magic TableJen then? It's kind of similar to LVM's TableJen, except that it's specific for Clang, of course. So remember, for LVM TableJen, TableJen is used to describe like characteristics of the target you're compiling for, like register files or instructions, selection patterns, all these kind of things. And Clang TableJen is basically to describe things that are specific for a front end. So for example, we use it to describe attributes in a concise way, and then we generate C++ code to handle different attributes in various places. As you've already seen, we are also using TableJen to describe all the different diagnostics. We're using TableJen to describe all the options that Clang can take, because you might not realize, but actually option parsing is one of the major parts of the front end as well. And then there's like, if you have a lot of built-in functions for a particular target or a particular language, you can describe these in TableJen as well. Finally, a little bit about how you can test Clang. So once you've built Clang, you can run make check Clang, and it will run a whole bunch of Clang-specific tests. The tests are actually organized in two different sets. So we've got the Clang unit tests, which are just like little the unit tests that poke at specific functions inside the Clang source code to make sure that these functions continue to behave as they should. But by far, most of the tests live under Clang/test, and these are like little C++ programs which you can run with LVM lit, and they will test it. They will test various aspects of Clang. For example, first of all, that Clang doesn't crash on a particular input. Often, if you get a bug report, you probably want to make sure that you don't ever regress again on the same issue. So once the bug has been fixed, you also add a little test for that particular problem, so that we don't regress that again in the future. You can also add tests to make sure that whenever you parse a certain construct, that the corresponding AST node is generated. You can do the same for testing Clang cogent, basically, to make sure that certain LVM IR is emitted for certain constructs. And also important for Clang is to test diagnostics, basically, to make sure that if you give it a broken program or broken input program, that it's going to complain about it and give the right diagnostic. So I'm not going to describe or give a few examples of the last three of these cases. So how would you basically test a parser? This is basically how you could do that. So you run Clang with the -AST dump option. That's going to dump the AST, obviously. And then what you're going to do is you're going to run file check on that to see if you've got certain interesting elements occurring in your AST dump. So, for example, for this input program, we want to make sure that there's a function decal with a name factorial, and then the next one should be a parm for decal to make sure that the parameter is also dumped into the AST, that we have a corresponding AST node for that. Then we want to make sure there's a compound statement, an if statement, two return statements, and so on. The key thing here is to not put a whole AST dump and just copy it into the test and add check lines for that. You just want to make sure that only the key elements are being tested, so that if something changes in the way AST dumps are produced, that you don't have to update like thousands of test files, but just like put what's interesting for this particular test and what you want to be tested with this case, basically. For this is so actually these things are. Sorry, the question was like, what's the difference between check and check next? So this is some kind of file check thing. I think there's another tutorial about testing. So they might cover file check. Basically, I can just give you a brief answer. So the idea is like, for the function deco, we want to make sure that on the next line there's a parameter variable declaration, and then a compound statement, if statement. In between the if statement and the return statement, there's some other nodes that we don't really care about in this test for some reason, for example. So that's why you just do a check, another check next.
Okay, so check next doesn't skip anything, it has to be next.
Correct, yes. To test cogent, can pretty much follow the same approach. So, but instead of dumping the AST, you emit LVM. What's important is that if you want to test Clang cogent at least, is that you disable optimizations, because you don't want to like write a test and then later someone else commits a tweak to an optimization and suddenly your code is going to look completely different. You just want to make sure that whatever Clang cogent generates is correct, basically. And whatever happens after that, that's not your problem, basically. That's the problem of whoever writes optimization passes. So what we've done here, pretty much the same idea, put some checkline stuff that we're interested in. So we want to make sure that there's a definition for the factorial function. Maybe in this case, we want to check that there's a compare instruction. You can use some magic regular expressions to make sure that it all matches up nicely. That's all part of file check. So if you're interested in that, go have a look at file check to do that. And last but not least, the diagnostics testing for Clang. So Clang has a special mode for testing diagnostics, which you trigger by running Clang -verify. And if you pass -verify to Clang, it's going to change the behavior of Clang completely. So it's no longer going to try to compile anything or emit any code. It's just going to run the front end, basically, parse stuff, do semantic checking, and after that, it's kind of done. And this is to show that, or to test that Clang is actually emitting diagnostics. So in this example, I've introduced a problem on line 2. You can see there's an extra t after int. And on line 3, I put a special annotation, expected error, cannot parse comparisons on Tuesday. So the expected error annotation is going to be interpreted by the -verify option. And that will basically tell -verify like, oh, on line 3, you're going to see, or if you don't see an error, then Clang -verify should fail. So, well, hopefully Clang is actually not going to emit this error, of course, because we want to be able to parse comparisons any day of the week, not just on Tuesdays. So what will happen if we run this through -verify? Well, it's going to report 2 problems. So the first problem is like, it's expecting a diagnostic, but it hasn't seen it, which is the one on line 3, which is about the cannot parse comparisons on Tuesdays, which is correct, because if you run Clang, it's not going to produce a diagnostic. So, but you just told Clang Verify, like, I want to see this diagnostic, and it's not seeing it, so it's therefore reporting it as an error. The other problem was the mistyped return type on line 2. It's saying diagnostic seen, but not expected. So if you run the program through Clang, it will emit a diagnostic for int t, which is not a valid return type. But we didn't instruct -verify that there's actually, should actually expect a diagnostic there. So it's like, oh, I'm seeing this diagnostic now, but I wasn't expecting it, so you better fix Clang or fix your test. In this case, we should rather fix our test. So if we fix the test, it would look like this. So we still keep the same typo on line 2, basically, but we now we put this extra expected error tag, saying that, oh, this is an unknown type name. Did you mean int? And if we now run this little program through -verify, it will pass basically. And your test is happy, and you're now testing that unknown type name diagnostics are emitted. And if someone ever changes this diagnostic for some reason, then your test will fail or start failing. Right, so that was pretty much all we had. There's some more information. There's a lot of information actually on the internet where you can get a closer look at things. So if you just want to get started hacking Clang, basically, the first two links are going to be really helpful. If you're a little bit more interested in like how the internals are organized, there's internals manuals. There's a good introduction to the AST as well. Actually, for file check, as the earlier question, there's a nice guide as well, manual. And there's
Yeah,
bugs.
so now that we explain you how Clang works, please help us to make Clang even better. And we do have a lot of bugs. We have more bugs than what we can fix. And not all of the bugs are actually tricky. We have some simple bugs. Particularly, we are tagging some bugs as beginner bugs. Those are expected to be simpler to start with. However, it might not always be tagged in adequately. And if there are any experts here, please remember to tag simple bugs as beginner, so people that want to start working on the code base will be able to see them, and hopefully will be able to start contributing. And yeah, if you have any questions or problems, feel free to ask me or Sven for help.
There's a question over there.
Why the deviation verify rather than just file check for the diagnostic messages?
So the question is, why would you not use file check but -verify instead?
Yeah, maybe.
So I would say -verify is kind of more intuitive than just running a file check. So it's basically going to tell you exactly what went wrong. It's like expecting this but not seeing this. If you were to do this with file check, it will be much more difficult to find out what's going on, because you have to apply some kind of inverse logic. It's like the front end is failing, but actually it fails and you want to check that it's failing. So
I think something particularly for verify, what you can do, you can actually match line numbers. It will make sure that certain error occurs on this line number. You can do it with file check, unless you start checking file numbers in your check pattern, but that's not scalable. Whenever you modify your test, you will have to readjust all the checks. So verify is much more tailored to this kind of diagnostic checks.
I know it's not really designed for this, but can you and are people using Clang -verify to give users of libraries consistent error messages in those tool chains? Like if I want to make sure that my error message says constraint not met for something somebody does wrong in my library, is anyone using it that way, and can it be used that way?
I'm personally not aware of that, but it's not a totally ridiculous idea to do, I think. So.
Thank you very much. I always find these talks very informative, because every time you hear this, you learn more each time round. One thing I picked up, which surprised me, I had not realized that the Clang recursive descent parser backtracks. And you're always taught at university that never use backtracking in a recursive descent parser because it makes performance unpredictable, and there's the nightmare of tearing down information as you backtrack, and you're doing semantic information. And it puts your performance out of the window. Could you explain a bit more why the Clang parser has to backtrack? Because it seems a bit unconventional.
Yeah, I'm not sure if it's actually traditional backtracking. I think it's more sort of obviously when we are trying to match the next rule, grammar rule, we might have multiple that will apply. And the idea is you're supposed to look at the next tokens really to decide which ones, but some of the grammar rules are, especially for some dialects are a bit more complex. Do you want to answer the
I know
question?
the answer.
Okay, great, yeah.
But I have no answer.
No, traditional parsers, like for C, are what's called LALR1 grammars, which means you can look at the next token and know which grammar rule you're descending down. C++, you have to backtrack because there's most vexing parse is the key word to look up. You have no choice in a C++ parser to have some kind of backtracking.
So can you comment on the immutable property of AST? Why is that?
Well, I think it's just a matter of that's how it happened to be. I do know that there was this effort of running optimizations on Clunk and being able to modify things a lot more, but as it never actually happened, people didn't actually develop that side. It has never evolved in this direction, as LLVM IR is actually quite suitable to modifications. But in AST, we actually never built this infrastructure, so I think.
It might even be historical. I'm not sure if people in the room are better suited to answer this question, actually.
I'd just like to make a small comment on that. We use Verify in the Clang statistical analyzer to check whether we have the correct value set on certain variables while the analysis runs. And we use it extensively, actually. So, yes.
Mm-hmm.
Cool.
What is the representation of a template, function definition, sequence of tokens, or an AST? And then how do you specialize that? Just modify the AST?
Yeah, so template have a special AST node to represent template function. It's not going to be function and something. It will be a template. And all of the parts that are dependent on the template parameter will be special dependent types. And then there is a special kind of part of Clang that is called tree transform. And that's the one that is going to look at all these dependent types and dependent things in the AST and create the instances of concrete elements.
Hi. So just a note on immutability. Part of the reason why Clang likes to have immutable AST nodes is it allows us to form canonical forms for things. So we will reuse the same AST node in certain cases, like between instantiations of a template. The non-dependent parts will generally try to reuse the same AST node, and you can't do that if the AST is mutable. And there's various other places where we do that, like in types, we'll canonicalize and reuse the same type. And for expressions appearing in the signature of a function template, we'll canonicalize and reuse those. So mutability will create problems for all of those layers.
Makes sense.
Thanks.
Yeah, thanks.
I've seen a node called implicit cast node in the AST that you showed. Can you explain a little more about that? Why that casting is necessary and so on?
In C type languages, you have rules like implicit conversions. So if you, for example, have an operation of types that aren't the same type, let's say you have a binary operator, maybe add two variables, and one is int type, another is char type. Then what happens is the operation have to be performed on the same type. So Clang will perform implicit conversions. So that, for example, the case when you will have this implicit expression, implicit cast expression added.
Any other questions?
Yeah, maybe I just talked about a silly question. So why do people use the manual and created the parser instead of some parser generator to handle the parsing?
So can you repeat?
Okay, and why do people use a manually coded parser instead of using some parser generators instead?
Actually, the main reason I think is for better diagnostics. Like automatically generated parsers are quite tricky to like give proper diagnostics. I think that's only one reason. There's probably many more reasons for doing the manual parser. That's at least one reason I'm aware of.
I think one great thing for Clunk, I have to say, it's if you're developing dialects of C and C++, it's much easier to look at handwritten parser and modify it and do a lot of like extra bits. And if you're also adding extensions and things like that, I think it's much easier.
Okay, I actually have a question.
Sure.
I was wondering if Clang offers any facilities to assist C++ developers in handling error explosions and stuff like that I might not know about.
Oh, and what kind of, like?
I don't know, anything to manage the error explosion or anything like that.
It's an
You
interesting
mean
idea.
like if there's a typo in your template?
Any special flags enable
Right.
certain different modes or anything? I'm not sure.
Like you would see more concise representation.
Sure, anything along those lines.
It sounds very good idea.
I think it's actually doing some. It's actually trying really hard already to like not give you screens and screens full of garbage basically. I'm not particularly working on this. I'm not sure if anyone else in the room knows more about this area.
But it's probably interesting area to look at, but I don't know if there is much happening.
As with any open source project, patch is welcome.
Yes.
Thank you. Anyone else? I guess that's all, so we can thank the speakers.
Okay.